Okay. So, come to your example 4. So, a 3-phase line is supplied by suspension string having 3 units. The voltage across the units nearest to the line is 20 kV and that across the adjacent unit is 15 kV. Find A, ratio of the capacitance of joint to capacitance of disc, B, system line voltage and C, string efficiency. So, it has given support suspension string that 3-phase line 3 units. The diagram is similar to example 3, diagram is similar, but numerical data other things are different, but this is a similar diagram for this example also. So, that is why arrangement is similar to figure this example 3. Now, let the capacitance between each joint and the metal work be Kc. So, this we know that it is we have to find out the K first, right, Kc. Now, first part is you have to find out the ratio of the capacitance of joint to capacitance of the disc, that is K you have to find out. So, V3 is equal to 20 kV, that is given here 20 kV, right, because the voltage across the unit nearest to the line is 20 kV, that means diagram is same. So, this V3 must be 20 kV nearest to the line is 20 kV and adjacent unit this one it is given 15 kV and that across the adjacent unit is 15 kV. So, V2 will be 15 kV. So, V3 20 kV, V3 V2 15 kV, these data are given, right. Now, following the same thing, you please write the equations, right. The way we have earlier written that same thing P and Q, apply your KCL. I am not doing for you all these things, this simple thing you please do it. If you do so, then you will get your what you call for this problem your this one V3 actually you will find V1 k plus V2 into 1 plus k. You will get V3 is equal to your V1 into k plus V2 into 1 plus. Same way you put KCL at point Q, same way, right. Then you will get, because omega c will be cancelled on both sides. So, nothing is written here. If I write omega c V3 is equal to your, I mean it is okay, hold on, let me make it for you. Suppose you have this one, your same diagram I am drawing for you, but one I will show, other one you can do it. Right. This is C, this is also C, this is also C and this one, and here this is your Kc, here also Kc, right, and this voltage is V1, this is V2 and this is line and this is V3. This is your line and this is C, 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 right, and current is going here, going here, going here. So, when you write the equation, so current to the voltage across this is V3. So, this current is omega c V3 is equal to this current plus this current is omega c V2 plus now this current. So, that means this current is this voltage here means this common point, this one, this voltage is V1 plus V2, that means plus your k omega c V1 plus V2. That means omega c will be cancelled on both sides. Therefore, V3 is equal to V2 plus k V1 plus k V2. That means V3, sorry, let me move it up. That means V3 is equal to your what I am writing, that V 1 k. So, for this term I am writing first V 1 k plus you take V 2 common, then 1 plus k. This is the equation, right. So, that way you can find out that is why I have written, that is why I have done it for you. That is why first one you can easily write V 3 is equal to V 1 k plus V 2 into 1 plus k. This is equation 1. Similarly, you please apply the way I showed you. Similarly, you apply here KCL at P point also in terms of k, then you will get in that case V 2 is equal to 1 plus k V 1 you will get, right. So, this is actually equation 2. Therefore, this V 2 you substitute here, V 2 you substitute in equation 1, V 2 is equal to your 1 plus k V 1 you substitute here. If you do so, then this V 3 is coming here. So, it will be V 1 k and you are substituting V 2 is equal to 1 plus k V 1, it will be 1 plus k whole square into V 1, right. Now, V 3 is given 20, V 2 is your is equal to V 1 k, then your this V 2, this V 3 is given 20 kV, this is given, and V 1 k putting in this equation V 1 k plus this V 2 is 15 into 1 plus k, right. This one we are putting. Now, V 1 k is equal to 20 minus 15 k, this equation. Therefore, V 1 is equal to, we are writing 5 minus 15 k upon k, this is equation 3. Now, it is same thing here also you should have, but I have written it, but V 2 is equal to 1 plus k V 1. So, 1 plus k and V 1 is equal to 5 minus 15 k upon k. So, 1 plus k into 5 minus 15 upon k, that means this your what you call this V 1 we are substituting in this equation, equation 2, right, equation 2. Therefore, it is a quadratic equation. So, 15 is equal to, because V 2 is equal to 15 is given adjacent, because lowest unit voltage is 20 kV and adjacent to that is 15 kV. Therefore, this your V 2 is equal to 15 kV. Therefore, this is a quadratic equation, you simplify. So, you will get 1 minus 5 k minus 3 k square is equal to 0, or other way I am writing 3 k square plus 5 k minus 1 is equal to 0. This is equation 4, right. Therefore, you solve this equation, you will get two value, one will be k is equal to 0.18, another is minus 1.847, but this is k cannot be negative. So, this value you ignore, you will get k is equal to 0.118. This is the answer for the part 1, right. Now, B it is given that where is that problem here? B it is given that you have to find out your not this one, example 4, this one. B actually you have to find out system line voltage is B. So, in this case B is equal to V 1 is equal to V 2 upon k plus 1, because we have seen this one V 2 is equal to 1 plus k into V 1. So, it is 15 upon 1 plus 0.18, right. So, it is coming 12.7 kV, and line to neutral voltage V 1 plus V 2 plus V 3, you sum it up all, V 1 is your 12.7, this is actually V 1 we are writing at the end, it is V 3 writing first 20 plus V 2 15 plus this V 1 12.7, it is coming 47.7 kV. Line to line voltage multiply by root 3, it will become 82.6 kV, and C is the string efficiency. So, line to neutral voltage is 47.7 divided by 3 into 20, because lowest unit voltage is 20 kV and there are 3 disc 3 units. So, 3 into 20. So, it will come around 79.5%. So, this is the your what you call that your string efficiency, right. Now, next is alternative method. Now, the following method can also be used to calculate the voltage across any unit and the string efficiency. Actually, a string of insulators may be considered to be equivalent to a transmission line with receiving end and short circuited your what you call receiving end short circuited and earth. That means your when you rather than taking this conception, you can consider that it is a series of capacitance in a transmission line connected and short circuited at the your receiving end, and the shunt capacitance are also there, as if it is something like your line to your ground capacitance, right. This way it can be imagined. So, if we do so, suppose you have a the n insulator in the string as shown in figure 12, it is made like this. For example, imagine this is a sending end and this is a receiving end, right. Sending end means the conductor is here actually, and this is your nth unit in the string insulator, and this is n minus 1, then some value x, some number x there, then it is that your near the your what you call the tower end, it is 1, right, as if it is a short circuited earth, and these are all Kc capacitance, as if your shunt capacitance, right. This way you imagine, and voltage here, it is from the top of the tower we are going like this. So, this side actually short circuited earth means as if it is a receiving end, that means it is on the tower side, and this is on the line side. So, this voltage is V 1 from here to here, from here to here it is V 2, from here now one thing is there, you should not be confused with the previous thing. Previously across each thing we have taken V 1, this we have taken V 2, this we have taken V 3 like this, but for this thing it is V 1, and here total is V 2, from here to here it is V 2, and from the x number from here to here it is V x. It is not across each one, first one is across the first one, when it is this voltage, that means across these two. So, this is V 2 and so on. So, do not be confused with the previous examples or previous derivation, right. So, and these are all Kc value, right. Now, insulator 1, just I told you, is the topmost unit connected to the cross arm, that is why I told you it is the topmost unit connected to the cross arm, and your that is earth, and insulator end is the lowest to it attached to the line conductor. I mean this is conductor, this is a conductor actually. We imagine that is a long transmission line, the way you have done that your sending and receiving voltage calculation for the long transmission line, this is the same thing, right. So, and you did Vx is the voltage from here to here, as if for transmission line we have also done, no, find out the, suppose that voltage Vx at a distance x, here similar way let Vx be the voltage up to the xth unit, there it was at a distance x, here it is at your up to the xth unit from the top of the string. I mean this is the top of the string, means this is the tower side from here to here, right. So, from that we can write that this expression, you know that from your transmission line expression, not deriving here, these are known to you, because for long transmission line this expression, that hyperbolic expression we have made it, right, for distributed line parameters. So, this already we have made it, those who have taken the course, or even if you not have taken the course, you have studied in your inductance, that long line, short line and medium line with calculations, right, there you have made it. So, Vx is equal to Vr cos hyperbolic gamma x plus Z0 IR sin hyperbolic gamma x, right. This is equation 6. This is actually known to us, because from transmission line voltage calculation, right, we have derived it for long transmission line, right. So, where gamma is equal to your, say we make under root z dash y dash, there also we have seen this, right, gamma is equal, in general gamma is equal to root over y z. Now, z dash is equal to 1 upon j omega c and y dash is equal to j omega k c. Only thing is here actually you do not have what you call that inductance, it is a capacitance, right, but philosophy remains same. There you are using something else in terms of inductance, right, but here it is capacitance, but philosophy is same, right. Therefore, gamma is equal to root over z dash y dash. So, if you this 1 upon j omega c into j omega k c, because y dash is your j omega k c and y your z dash is 1 upon j omega c. Here inductance is not there, line reactance is not there, but philosophy remains same. So, gamma is equal to, finally it will come root over k actually. And another thing is that your end is short circuited, that is the tower end actually, that is short circuited, and that will be VR is equal to 0. That means this, as is short circuited tower end, we are thinking that we are receiving in voltage VR is equal to 0. So, if it is short circuited 0, that means put that thing in equation 6. That means in this equation you put, you please put VR is equal to 0 in this equation, you please put it. If you do so, then Vx will become Z0 IR sin hyperbolic x root k. So, in this case VR is equal to 0. So, this term will not be there, and here it is gamma is equal to root k, you put root k. So, it ultimately Vx will become Z0 IR sin hyperbolic x root k. So, that is why Vx is equal to Z0 IR sin hyperbolic x root k. This is equation 7, right. Therefore, at the sending end x is equal to n, look at the diagram, at the sending end, I mean this one, the same way you do know at the transmission line, at the end x is equal to L. So, here also at the same thing, at that your what you call at the sending end x is equal to n, because it is n number of disc is there. So, x is a number, not a length here, right, not a length here. So, x is equal to n, in that case you will find Vn is equal to Vx is equal to Vn is equal to V, because Vx x is equal to n means it will be Vn, and Vn will be equal to V, the total voltage. Vn is equal to V, I mean from here to here the total voltage Vn is equal to V. That is V1 plus V2 up to plus sum of all V1 plus V2 plus up to your Vn, right, all these things. So, Vx is equal to Vn is equal to V. Therefore, equation 7 can be written as V is equal to Z0 IR sin, because x is equal to n, therefore, sin hyperbolic n root k. This is equation 8, right. Therefore, dividing equation 7 by equation 8, you divide equation 7 by equation 8, you will get Vx upon V is equal to sin hyperbolic x root over k divided by sin hyperbolic n root over k. This is equation 9, right. From for mth disk, if x is equal to m, I mean for mth disk, look at the diagram, you have n number of disks, any disk which is called as mth disk, it is coming from 1, 2, 3 up to n, in between some x number is there. For any disk from here, say some mth disk, right, you substitute in that case x is equal to m, right. So, for mth disk, in this equation you replace x by m, it will be Vm upon V. If it is Vm upon V, then for mth disk it will become Vm upon V is equal to sin hyperbolic m root k by sin hyperbolic n root k, because here you have put x is equal to m. So, Vm upon V is equal to sin hyperbolic m root k by sin hyperbolic n root k, right. So, Vm upon V is equal to sin hyperbolic m root k divided by sin hyperbolic n root k, or Vm is equal to this cross multiplication V into sin hyperbolic m root k by sin hyperbolic n root k. This is equation 10. And for the m minus 1 disk, I mean just the previous one, if you have mth disk, then the previous disk, that applied voltage replace m by m minus 1. In that case, it will be Vm minus 1, replace this m by m minus 1 is equal to V into sin hyperbolic m minus 1 into root k divided by sin hyperbolic n root k. This is equation number 11. Look, here the equation is totally changed. Earlier it was omega c, then your what you call omega, then omega k c, all these things were there, but here it is in term, it is a most generalized one, and it is in terms of that sin hyperbolic. So, voltage drop across the mth disk, then Vm will be capital, do not confuse this derivation with the previous one, right. Here the voltage drop across the mth disk, it will be capital Vm minus capital Vm minus 1. This capital V and do not confuse, do not mix up with the previous one, here that nomenclature is just different. So, do not mix up when you will listen to this video or when you solve numerical. So, do not mix up. So, voltage across the mth disk, that small Vm is equal to difference between your Vm and Vm minus 1. So, capital Vm minus Vm minus 1. That similarly, if m is equal to your 2, 3, 4 like this. So, all the voltage across the each unit you will get. I mean across each, using this formula equation 12, across each unit you will get the your or across the each disk you will get the voltage, right. So, now in this case the string efficiency is equal to voltage across the string divided by n into voltage across the lowest unit n, right. So, voltage, total voltage is V, and the string efficiency lowest voltage means it is n, and voltage across the lowest unit will be Vn minus Vn minus 1, that means same thing. That means, in this case if you replace m by n, suppose if m is equal to n, the nth disk, the last one, then Vn will be equal to Vn minus 1. So, that is why it is written string efficiency is V upon n into Vn minus 1. This is equation 13. From equation 10 we get for m is equal to n. So, this is equation 10, this is your equation 10, right. In that case if you put m is equal to n here, then Vm will become Vm will become V, then m is equal to n means Vn will become V, because sin hyperbolic if m is equal to n root k and sin hyperbolic n root k, it will be cancelled and Vn will be equal to V. Therefore, from equation 10 if we get m is equal to n, then Vn is equal to V, then sin hyperbolic n root k is equal to V. That is equation 14. And for m is equal to n minus 1, if m is equal to n minus 1, then this same equation m is equal to n minus 1 if you do, then Vn minus 1 is equal to, then you replace this m by n minus 1 in equation 10, it will be Vn minus 1 is equal to V, then sin hyperbolic, then n minus 1 root k by sin hyperbolic n root k. This is equation 15, right. Therefore, string efficiency will be V. I mean this is the string efficiency V upon n into Vn minus 1, right. So, string efficiency will be your V upon n into V minus V sin hyperbolic n minus 1 root k divided by sin hyperbolic n root k. Therefore, is equal to, just simplify, sin hyperbolic n root k, because V will take common, V will be cancelled, sin hyperbolic n root k by n into sin hyperbolic n root k minus sin hyperbolic n minus 1 into root k 16. This equation is independent of the voltage V string efficiency, it is independent of this one, right. So, this is actually if you use your what you call that that most I mean if you imagine the line that is string insulator in each disk, if you imagine that it is a long line and no inductance is there, but capacitance is there in the line, that line capacitance, and shunt capacitance Kc is there. Therefore, and receiving end is earth side, that is the tower side, it is earth and short circuited. So, receiving end voltage is 0, and using the same your what you call that long transmission line voltage expression, you can get all the voltages as well as the string efficiency, and this calculation of course must be very correct one compared to this one, but difference will be too small. Later we will see the example, another thing. So, now come one example, right. A string of suspension insulators consists of 4 units. There are 4 units or 4 discs. The capacitance between each link pin and earth is 1/10 of the cell capacitance of a unit, that is K is equal to actually 0.1, right, because it is 1/10 of the cell capacitance of a unit. The voltage between the line conductor and earth is 100 kV, that is also given, right. Between the line conductor and the earth, find a voltage distribution across each unit B state. It is given that voltage between the line conductor and the earth, that means your what you call the total voltage, right. You have to find out two things, voltage distribution across each unit and string efficiency. Now, so this is the circuit diagram V1, V2, V3, V4, right, and because 4 units are there 1, 2, 3, 4, then you have Kc, Kc, Kc. V1, just let me tell you one thing, please do not confuse with other examples and other thing, because it have taken as a long line thing. So, please do not your this thing confuse with the previous one, you because here nomenclature is different than the previous one. These are all small v1, small v2, small v3, small v4. So, it is capital V1 is equal to V small v1, capital V2, that is small v1 plus v2, that means this is actually capital V2, capital V3 means this one is equal to small v1 plus small v2 plus small v3, and capital V4, that is total, is equal to your small v1 plus v2 plus v3 plus v4, right. So, do not confuse with the previous one, there should not be no space for your what you call confusion, everything is clear, right. So, arrangement is shown in figure. So, we know that Vx upon V sin hyperbolic x root k upon sin hyperbolic n root k, this is from equation 9 we have seen. Here n is equal to 4, k is equal to 0.1 is given. So, square root of k is 0.3162, and total voltage I told you it is given that the line conductor to the earth, that means the top of the tower, right, that is this thing where insulators is hung from, right. So, V is equal to 100 kV and x is equal to, there are 4 units, x is equal to 1, 2, 3 and 4. Therefore, V1 when x is equal to 1, right, this same using equation 9 is V into sin hyperbolic root k by sin hyperbolic 4 root k. It is given that if general formula sin hyperbolic theta is equal to e to the power theta minus e to the power minus theta upon 2, right. So, whatever it is, you just make V1 is equal to 100 into 0.3215 by 1.6302, that is 19.722 kV. Directly you can get it from calculator, no need, forget about this thing, directly you will get it, right. So, 19.722 kV, right. Similarly, using the same example, sorry, same expression, this one, put x is equal to 2, 3, 4. So, you will get V2 is equal to V into sin hyperbolic 2 root k by sin hyperbolic 4 root k, you will get 41.433 kV. Similarly, V3 you will get sin hyperbolic 3 root k by sin hyperbolic 4 root k, you will get 67.3224 kV. Similarly, V4 is equal to V sin hyperbolic 4 root k, this is same. So, it will be V 100 kV. Therefore, small V1 is equal to V1 19.722 kV, this small V2 it will be V2 minus V1, because from this expression I told you, this is V1, this is V2, V3, V4, this is capital V1, this is capital V2, this is capital V3 and this is capital V4. Therefore, you have to take the differences. So, V2 is equal to small V2 is equal to V2 minus V1, you will get 21.711 kV. Small V3 is equal to capital V3 minus V2, you will get 25.88 kV, and small V4 is equal to V4 minus V3, you will get 32.677 kV. That means this expression you can use. If you put n, it will be Vn minus this expression you can use, right, that is equation 12. So, with that we are getting V1, V2, V3, V4, all small V1, V2, V3, V4 you will get using equation 12, right, and this is your all the voltages. Now, string efficiency, this formula we know, this formula we have derived from this equation. Here is this is from equation 16, right. So, this is actually in bracket I am write down for you, this is actually equation 16, right. So, string efficiency, it will be sin hyperbolic n root over k by n into sin hyperbolic n root over k minus sin hyperbolic n minus root over 1 k. So, you know n is equal to 4, root k is known, n is known is 4, you substitute all this value. So, you will get approximately 76.5% the efficiency is, right. So, this is using the generalized formula using a long transmission line, I have one exercise for you when you will do this, that same example you find out your string efficiency and voltage across each disk using that your general method, right, and just compare the result. You will compare this result, you will compare this result with a general thing whatever we have done before. This is a generalized one, and that was in terms of Kc whatever we have got. You compare the result and see the differences, right. From your exam purpose, from your assignment purpose, please see the differences, whether you get any differences or not. String efficiency and this one, this is an exercise for you when you will do this thing, right. We will come more examples and our thing on insulator. Thank you now.